Thank you so much. First of all, I want to say thank you for the organisers and for Kieran for having me here. It's really great to be here and see so many people into quantum. When I started quantum computing as a student, and I got interested in it in like 2000-ish, nobody was interested in quantum computing, so this is definitely a great result that people are now. And today, I wanted to talk to you about, I wanted to talk to you about NVIDIA's vision for quantum computing and how we see our role as being critical in the development of large-scale, useful quantum computers. So when I tell people I work at NVIDIA and I also work on quantum computing, inevitably the first question I get, you can probably guess, is NVIDIA building a quantum computer? So I should deal with that question immediately. I've got a slide on it, so I'll answer it before you ask it. And the answer is that NVIDIA is not trying to build qubits. Lost some of my slides? That's fine. NVIDIA is not trying to build qubits. We're not trying to build physical quantum hardware, QPUs or quantum processing units, but we are trying to build devices that will turn qubits into useful quantum computing devices. And it turns out that doing that is not trivial and is not entirely a quantum problem. And so we have a vision that we're not building qubits, but we are building what we call accelerated quantum supercomputers. And this is some terminology I've just introduced, which I will explain. And in explaining it, I think it will do a lot to show you what our vision is and how we think that NVIDIA especially is critical in making that happening. So what is an accelerated quantum supercomputer? I have a picture. It's always the best way to explain something. So this is a render that kind of shows our vision for a device that takes qubits and turns them into a useful quantum computer. And what you're seeing there is an NVIDIA supercomputing system. So this is a DGX superpod, which is one particular architecture for how we build GPU supercomputers. And you can see on the left, those racks have got the GPUs in them. And on the right, there's an artist's rendition of a quantum computer. It's very artistic and intentionally non-specific. So it could be any quantum piece of hardware. It could be any qubits, I should say, any QPU. And you can see that, importantly, the quantum hardware is connected to the conventional AI GPU supercomputer. And this is absolutely crucial, because there's many reasons why if you want your qubits to do something useful, you need that hardware next to them. And I'll talk a little bit to that and what those reasons are, and also why, in fact, AI supercomputing is not only going to be useful in a final deployed machine to run it like this, but also is going to be critical to get us to this point in the development work that we're doing today. So, to talk to that, here's the two kinds of ways in which AI supercomputing is going to be really important for quantum computing and how we see NVIDIA's role as being central. So on the left, I've got an idea of what I just talked to with that picture, that if you actually have a useful large-scale quantum computer, it's going to need AI supercomputing inside it to do many different things you need to run the machine. So I don't necessarily want to go into too much technical detail, but if someone asks me, I absolutely will. But those things include quantum error correction, so if you want to run fast decoders. So to actually make quantum error correction work at a large scale and start to tackle useful applications, you need to be able to do measurements on your qubits. You need to take the data from that. You need to do some classical processing on a GPU supercomputer, and based on the result, take some action on your qubits. And you need to do that extremely fast. You need very low latency in the connection, and you need your algorithm to be run very quickly. And your kind of budget for that is typically like tens of microseconds. And we have a piece of hardware, a software architecture called DGX Quantum, that allows people to plug in control systems that might be specific to one particular kind of qubit into our GPU supercomputer and connect it to the QPU hardware, the qubits, and do that very fast connection, an order of magnitude faster than is currently considered necessary for a decoding budget. And so that, of course, is really critical for running your quantum computer. It's also kind of important that when we think of doing that, we use GPUs, because it gives you the flexibility to reprogram that decoding algorithm as algorithms develop. If you tape out an ASIC or you work with an FPGA, you're limited by that kind of learning cycle. You can't suddenly update it. You can't even switch it if you start experimenting with different kinds of qubits, like in a supercomputing center of excellence. So that flexibility is really important too. Also, if you look at how actual applications will run on a useful quantum computer, they won't just run on the quantum hardware, they'll be hybrid. So hybrid algorithms talks to the fact that a real application needs to send some of its computation to a GPU and some of it to a QPU, to the qubits. And even in sort of the future, when we think of fault-tolerant, large-scale quantum computers that you think of as being like the canonical quantum computer, even those applications still need classical co-processing as well. Even if you look at something like quantum phase estimation, which is the kind of go-to, absolutely brilliant if you can run it for quantum chemistry application, you need to sort of start that off with a warm start with something like a Hartree-Fock calculation, a classical calculation, and there's many more other cases where you need to do that. So GPUs are going to be critical for actually running useful applications, and co-locating them next to qubits will enable that. And also, we're super invested and obviously excited about, because it's in our DNA, about AI for quantum computing. So we're interested in how AI might actually enable some of those control mechanisms I've talked about, like decoding, or even things like calibration and readout, by developing AI algorithms that might be better decoders than the classical algorithms people already have. And that's a very active area of research, and we're just exploring that, as well as how you parallelize these things on GPUs in general. We're exploring that right now. And we partner very broadly, and if anyone here is working on that or interested in that, then we're very interested to work with you to make it happen. So that's deploying a quantum computer, you need GPUs, but also for developing the qubits and the applications you're going to run on this thing. So if you think about that, there's many different ways in which we think GPU supercomputing is, and will actually continue to be more so, the gating technology for development of quantum computing. So it's very familiar to people, especially in the NISC era, that quantum circuit simulations has been an important tool. But that's only going to get more important, I think, as we move into the error-corrected large-scale era. So we have a software platform that I'll talk about in a second called CUDA-Q, and that allows you to run circuit simulations, a state vector kind, but also tensor network simulations that scale up to much larger systems, and really let people start to see how applications will perform on the larger scale hardware that we are now coming around to accept that you're going to need to run useful applications. You also need GPUs to use AI to help actually develop applications rather than run the machine itself when you have it. We have some great work that we did with University of Toronto and St Jude's Children's Hospital, developing what's called the generative quantum eigensolver. So it uses GPT, like ChatGPT, but it trains a model not to predict words that will go in a sentence, but parts of a circuit that will build a circuit to perform some kind of application or working to some figure of merit you care about. And so that AI-generated circuit, it's quite technical to go into the details why, but if you do things that way, you actually have to use the quantum hardware less, even though you might think, well, to train it, you've got to run your QPU to tell it what the outputs are. It actually works out much more efficient. And then there's other things like actually building the quantum hardware. So it should come as no surprise, but it does surprise me to always think that NVIDIA, their new GPUs that we build today, we still simulate those GPUs on a GPU supercomputer when we design them. And so, this is a highly refined technology where simulation is still the key tool to make the hardware. It's also true for qubits, for the quantum hardware that will sit in that accelerated quantum supercomputer. So modeling noise in that hardware and actually dynamically simulating the actual physics of it to make the qubits better, to make them perform well enough for error correction to kick in and work, is also something that needs GPUs. And so that's why we see what we do as naturally fitting into quantum computing and us playing a critical role. And that's what we've been doing. So we've been going out, we've been working with supercomputing centers to bring these tools to the researchers that need them to take us to useful accelerated quantum supercomputers. So I've just called out here 2 examples of collaborations we've had, one in Japan, one in Denmark, with AIST in Japan, and with Gefion NNF in Denmark, where we've put thousands of GPUs in there which are being used for quantum applications. So people simulating applications, quantum researchers to develop them, and that's where we're really building quantum communities and ecosystems around those tools to enable the development of quantum computers. And to go back to the first thing I talked about, actually having GPU supercomputing in a quantum computer when you've got one, and thinking about those challenges, we've also been partnering up supercomputing centers with qubit vendors, QPU hardware builders, so they can put those 2 kinds of hardware together and start to think about how they might connect to each other to do those things like error correction, control, calibration, readout. And in fact, a real flagship one for this is that we've worked with Quantum Machines, who have taken our DGX quantum architecture put their OPX 1000 control system in the top so it can connect to, say, superconducting qubits, and they have the Israeli Quantum Computing Center where they're actually bringing in different kinds of qubit technologies and experimenting on error correction. And the thing that stands out in this slide that is possibly one of the key things about how we work is there are many different kinds of qubits and different qubit vendors on that slide. And that's because at NVIDIA, we believe that, well, our approach is, and we believe that an accelerated quantum computer needs to be at this stage qubit agnostic. So we are not committing to one kind of qubit or one qubit vendor because, I mean, everyone's doing great work and we want to work with absolutely everyone, but nobody knows yet what the qubit in a useful accelerated quantum supercomputer will look like, or even if there'll be more than one kind of qubit. But what we do know is that to control and make those qubits into a useful device, there will be NVIDIA hardware. So in that sense, we've de-risked the problem by being the people working on the challenges that everyone faces and by enabling people access to every one of those kinds of qubit technologies. So, here we go. So this is just a slide to show our partner ecosystem. So we partner really broadly, I've made that point. And the reason I wanted to sort of finish on this is just so that, to make the sort of call to action that if you're interested in working with us in any of the areas I just talked about, or you have other ideas, this is our bread and butter. So we want to work with everyone, we're open to everyone, and we want to bring everyone's capabilities to other researchers too. And we do that in a number of ways. One thing I hadn't talked about that much was our software platform called CUDA-Q. That's a platform that lets people run very, very fast GPU-accelerated simulations. It has a programming model that is, similar to other frameworks you might use, but is written hybrid first. So you can start writing applications that do talk to quantum and classical hardware. And moreover, as well as being able to simulate quantum hardware, we have a huge number of QPU vendors that can plug their backends into that. So you can experiment with different qubit modalities. And all the code that you write is de-risked in the sense that it is not tied to one particular qubit vendor or technology, and also can switch seamlessly between fast simulation and actual hardware. So I think I've probably run up against my time exactly. That doesn't normally happen. This is fantastic. I might have a minute or two, though, if I'm obnoxious and just stand around. So if there is a question or two, and it is okay for me to do that, I'm happy to try and answer them if I can. Thank you for your time, though. No questions is fine as well. I'll take that. Are there any questions? Yes?
So in terms of the way you guys are arbitrating the data, does it actually have to pass through, what's the pass-through order of operations? Is it actually going through the supercomputer first, or is it going through the quantum space first? How are you guys arbitrating?
So it depends on in what ways you're thinking. The question was, how does the data, what's the process where the data goes through? Does it go through a supercomputer first before a quantum computer? Is that, so, or the other way around? So that question kind of, how the two work together depends entirely on what you're talking about. So if you're talking about the fact they both sit together in a final quantum computer and the supercomputer is helping run the qubits and do things like error correction, that's like a tight loop between the two. And so data goes both ways, it needs to, right? But if you're talking about programming a hybrid application that's going to run on both, then it really is, you write at a high level, and in our CUDA-Q software platform, there's a kernel kernel framework that lets you declare what will go on which, very trivially, and then some of it will go directly to the supercomputer, and some of it will go to the supercomputer for compilation and whatnot, and then eventually go through to the quantum computer, the qubits.
Do you guys still have your typical CUDA load balancing frameworks or libraries within that?
Yeah, so CUDA-Q is like high-level platform for people to write the code. Under the hood of CUDA-Q, there's two things that are really performant. So if you're running the simulations, we have Q-Quantum. So these are like lower level. You probably don't need to interface with these. Q-Quantum also powers most of the other computing frameworks, quantum computing frameworks for GPU acceleration. So we have a direct connection to that super fast when you're simulating. And then on the other side, if you are, say, part of your hybrid algorithm wants to run on the normal supercomputer, that all uses the CUDA-X libraries. So that's like the fastest way you can do like linear algebra in parallel. So the other real advantage of our software platform is that it builds on so many years of experience in enabling the revolutions of scientific computing, AI, machine learning as well. Did that answer your question with not too much marketing blurb, but actual information?
That's interesting. If you guys have any literature, you guys can...
Yeah, come and find me and we can definitely talk about it. Awesome. Can I take one more, or do you need to crack on? You sure? You sure? I'll take one more. Okay, no, you convinced them not to ask. There you go. Thank you so much for your time. Have a great day, and come and find me if you want to talk about any more.